Hi, I'm from the University of Edinburgh. We have a relatively large translation group, about 16 full-time people working purely on machine translation systems. And one of the big things in Europe is the Conference on Machine Translation, where every year the community gets together and evaluates quality of translation systems. This year in 2017, there were 103 submissions from 31 different institutions. That summed over all the languages. There were 14 total language pairs, so that's 7 in and out of English. We only do in and out of English currently. And this has been running for several years, like there's far more years than that. But the point I want to make on this slide is if you look at which system won in each of the language pairs that we ran, then before 2015, no one with a neural system was even really submitting. And then starting in 2015, you get neural wins in one language pair, but phrase-based is still dominating. There's this Russian company, Prompt, who does rule-based machine translation, and they were winning the rule-based category for one direction on Russian. But come 2017, it was all neural systems at the top. And really what's happened is partly it got better at lower resource languages, but also it just got better in general, and there's been a flurry of papers about how to improve it, and I will give you some high-level points about the differences. The first thing is a neural system can read the entire sentence before even deciding what to generate as the first word or any word in the sentence. So it's seen the entire source, in this case a Czech sentence, and before it generates the word he or it at the beginning, it has read the whole thing and seen the word brother there, and it can insert a male pronoun. And generally, a neural machine translation system is better at these long-distance agreement problems than a phrase-based system. It's not perfect. In fact, there tend to be problems where it overgenerates male pronouns versus female pronouns. A very common problem with a lot of neural networks in general is they tend to over-exaggerate biases that exist in the data. So if you have any imbalance in the use of the two pronouns, it's going to pick the one that dominates in that case. The same sort of thing happens with formality. If all of your training data is bureaucratic and formal, then you have a very hard time generating personal pronouns. I or you even is not going to happen often in text, and therefore it becomes difficult to produce that. But really the difference between phrase-based and neural approaches is that they can make decisions based on the entire sentence, not just local decisions based on part of it. Phrase-based systems tend to forget things after 3 or 4 words. Another thing is word choice. Neither of these is actually a perfect word choice. In this example from German, the reference says up and coming, and neither of them actually generated that, but I would argue that young is probably better than offspring in this example. And all of these you see, by the way, are actual submissions to the Conference on Machine Translation. So someone made a competitive phrase-based system, and someone made a competitive neural system, and I'm comparing the outputs. Different teams in many cases, so it's not quite comparable, but it's the same training data in theory, and both people were trying to get the highest translation quality. And generally, we see this trend that neural machine translation really improved the fluency, but it didn't improve as much on the adequacy or being a correct translation. And in fact, it's somewhat more dangerous in a sense, because humans, when they read this sentence, they look at it, and if it's disfluent, they trust it less. But if you can produce a fluent translation that has nothing to do with the input, they might still believe it. So we actually have to do more work on improving the adequacy and accuracy of the translations. And in a sense, it could be more dangerous, but it's also generally a better translation if it's actually fluent. A lot of the errors you'd end up correcting are disfluencies that someone probably could have pieced together if they wanted to, but it just sounds bad. Another thing that plagues all forms of machine translation is that rare words are really hard to translate. If I've only seen something in the corpus once or twice, in a neural machine translation system, I have to estimate 1,024 floating point numbers from one little piece of evidence that happened somewhere once in the corpus, and that's not going to work very well. So neither of them is getting this word pigeonholed correct in the translation here. You can argue about plugged in drawers versus put in drawers. Neither of them is really the right thing to do, but the point is that translations covering your terminology are still quite important to have as training data, because in the natural world on the web, I'm very unlikely to see your specific terminology in the training data that I collect. Neural machine translation is also much better at matching style. In a sense, it overfits style. So in this example, there's a Turkish to English system, and Turkish English only has about 200,000 sentences. We consider that to be a low resource language pair, though there are varying standards for what low resource means. And in this case, it translated as, my brother was harmonized in every situation. And you can imagine what sort of bureaucratic text would have produced that a person got harmonized in a situation as opposed to going with the flow or went with the flow. And I could totally imagine that MT at EC, we haven't tried this, would produce a translation that has someone being harmonized. Sounds like they were sentenced to something, but. The moral of the story here is if you have in-domain data, great, because it will actually try pretty hard to fit the style that you have. And that could be as little as 10,000 sentences that have been translated in domain, and you'll get these stylistic matches. It can start sounding like a financial news reporter, and it translates the word stock into French as an actual financial stock, as opposed to a pile of things, which is an ambiguity in English. But it's also really awkward if you don't have in-domain data. And the canonical example of this is for a lot of languages, you have the Bible and movie subtitles. And if you throw movie subtitles into your system, it starts swearing a lot randomly, because open subtitles is available. We actually had to take that out when I was working at Bloomberg. We didn't want the open subtitles in there anymore, even though there was a fair amount of data for that. And the Bible also has weird language to it, where you get Joe and his 5 apostles went to the grocery store. This is actually a huge problem. Most people don't bother with the Bible because the language in it is so weird and it's so out of domain for what they want to do. I'm working with isiXhosa right now in South Africa, and while it's an official language, there's actually very little parallel corpora for it. And in fact, the Bible is the largest parallel corpus we have for isiXhosa, and that's causing us interesting problems when we want to talk to people. I actually know the guy at Microsoft. When they did a demo of their machine translation system, he wrote a swear word filter so that the CEO's demo would not swear at people live at the conference. All right, so let's talk about some data sizes. Phrase-based machine translation has a reputation for working better on low-resource languages. Not great, but better than neural machine translation. Or put another way, neural machine translation has a reputation for being data hungry. And earlier, it was about 10 million words to have a better neural machine translation system than a phrase-based system. We've since improved our systems a bit, and there's been a whole bunch of work on tricking things and special measures that you can do, dropout being one of them, to work on lower resource languages. The real difficulty is if you've only seen a word once or twice, then how are you possibly going to learn a 1,000-dimensional vector of floating point numbers for that? There's just way too many parameters and way too little data to actually learn something reasonable about that. So people have done some work on how you tie things together, how you might make use of a lexicon for a lower resource language. And now, if you follow all the tricks in this paper I'm citing here, at about 200,000 words, you can get a better neural system than a phrase-based system. And we're still actively working on this problem. We're looking at about 100,000 words for the Izikoza case, and 800,000 words for Tagalog and Swahili right now. That's actually a US government-funded program where they care about low-resource languages. And in fact, this one is also a US government program that has been funding, looking at Uzbek and a lot of other smaller languages that don't have the same official status in the EU, where there's a lot of parallel corpora comparatively. The other thing is, how much in-domain data do you need? So at about 10,000 words, we can measure the quality of our system on your data, which is not actually helping get anywhere in terms of improving quality on that. For 50,000 words, we can do what we call fine-tuning, and neural networks people are really great at coming up with fancy-sounding terminology like thought vectors and neural networks for that matter, as opposed to autoregressive encoders or something, which sounds technical but not fancy. But fine-tuning is one of these very nice sounding things where basically what we do is we train on your data last. And the reason we do it last is it emphasizes that data more at the end. We can give it a little bit more weight. And often you build a base model and then fine-tune on whatever you want to do. If we do that for news, for example, that buys us about a blue point. If we do that for medical machine translation into Polish, for example, that buys us 6 blue points. Part of that is we have a lot more English-Polish medical data to do the domain adaptation with, and part of that is we didn't actually have much in-domain data naturally occurring in the base corpus for Polish. So adding that little bit helped a lot. The same thing is true even if you just have monolingual data in your domain. What we can do is we can take your monolingual data and translate it with a machine translation system back to the source language. And then we get this data that's some possibly quite bad, say, English, but fully correct German. And if we have that monolingual German, we can add it to a English to German translation system, and then it will learn to translate from bad English to good German. And that's still a workable plan if you have monolingual data in German, in this example. And of course, that extends to any language. As long as it's in your target language, we can improve translation quality just exploiting monolingual data. So I'm going to move on to a case study. I don't know if anyone is from the European Patent Office. If you are, it's going to be a fun talk. And let's talk about patent translation. So patents have a very weird terminology to them. Apparently I have 2 patents. I can't actually understand what I did from them. But the European Patent Office made a deal with Google whereby they gave their translations, which is millions of words, to Google. And all Google did is they added it to their generic translation system. There is no Google Translation for Patents product. There is only Google Translate with the European Patent Office data added to it. They've also refused to share this publicly. I have asked them, ELRC has asked them, and they have not given us the data. But the World Intellectual Property Office, because they're a fellow patent agency, has shared has EPO's data through a sharing agreement that's actually embedded in the European Patent Convention. And what they did instead is they hired an academic consultant, Marcin Janoswiez-Dalmont. Sorry, Polish people, I'm horribly mispronouncing his name. And they got a custom translation system, and Marcin actually worked with us for a while, and he was consulting for them while he was in Edinburgh and while he was at the University of Poznan. So let's look at the results here. We can compare the Google translation system to the WIPO custom translation system built on what we think is the same data. It's just that the system was specifically customized for patents. And for all of these languages, I've got Chinese English, Japanese English, Korean English, and French English. You can see that the blue bar is higher than the red bar. And we can compare with Google Translate. That's fairly straightforward. We can send the same text through them. And we can see exactly what the EPO got for their data through this deal. And we can also see what they could have gotten by building another system using a European solution. And in all of these cases, the scores are much higher for a custom translation system. This is partly the justification for MT at EC existing, not just intellectual property rights, not just preserving the privacy of your data, but by having a custom system that's built on your data and tuned for your data, you get better translation quality. So another thing to note is actually WIPO launched neural machine translation on their website before Google did. And people were asking WIPO, can we license your system? And in fact, because they're a UN agency, they're providing pro bono translation support to the United Nations as well. So let's summarize the European Patent Office here. They gave their data to Google. We don't know exactly how much data, but several 100,000 high-quality translations of patents. That's a quote from their press release. We know that the solution they got in return is inferior by, on average, across all the languages, 6.4 blue points. We consider one blue point to be publishable, so this is big. Quoting part of the European Patent Office mission back at them, they're meant to support innovation, competitiveness, and economic growth across Europe. That is literally part of their mission statement through something about the European Patent Convention. Keeping in mind that there was a superior European solution available the entire time. And actually, according to the European Patent Convention, Article 14, patents are public. The whole point of a patent, literally the word patent means that it's a letter from the government saying that you have exclusivity over something. And by law, these are public. I don't care about the applications that are in process and are secret, blah, blah, blah. I just want the public patents that are translated and corresponding with each other. And actually, unfortunately, I'm not sure, maybe there are some lawyers in the audience, whether they're subject to this EU public sector information stuff because they're their own patent convention. But they do have this nice clause here that says, at least in theory, they should be publishing these translations. Press at epo.eu or org. So, moving on. I like getting data, and actually I'm here partly to advertise that I'm from the Paracrawl project, which is coordinated by Edinburgh and funded by people in this room. And it is a project to crawl the web for as much parallel corpora as we can get. We're working on all 24 EU languages. Hi, Norway and Iceland. We're putting in a proposal for you, so please fund us in the future. And the project started in September. This is a pretty new project, 18 months. We will have our first release come January for 12 languages. These are essentially the 12 easiest languages for us. Slight pedantic detail here is that 24 EU languages includes English, so it's actually 23 parallel corpora that we'll get into and out of English. And I remember in actually Josef's presentation, I believe that was 1 billion total words for all of ELRC, and we're promising to do 1 billion words for each of 8 languages, including English, and 100 million words we are aiming to get for the other languages. I'm not sure we'll get Maltese and Irish and some of the more difficult lower resource languages up there. It really depends on how frequently they're used on the web. But that's our goal, and we're going to dramatically increase the size of data available in the ELRC share repository for translation. The goal of this project is not to get your in-domain data, it's to get a better base model, a much stronger system from which we can start that is probably out of domain for you. For Irish, it might be quite in domain because honestly, a lot of the translated Irish comes from the governments, for instance. And sometimes we get Canadian government stuff thrown in there. We want Canadian government for French. That's still worth having, but we're aiming to have all the 24 official languages by March 2019. We're posting this on our website, and we've already got monolingual data for just about, well, for 130 languages posted on our website, monolingual, that we've extracted from Common Crawl. It's everything that we have a language classifier for. We run the language classifier, post it online, and it's free to download and stuff. Okay, so since I'm at the ELRC conference, during the contract negotiation, we actually had a fun attempt to insert a clause where they said, we want you to review 3% of the corpora manually, but that's a problem for us because 3% of 1 billion times 8, or 3% of 8 billion, is actually quite a lot of sentences that we would have to review. So, we calculated it would be more than the entire budget of the project, which is great that the EU actually agreed to have 2,000 sentences per language, but now I will use this pulpit to lobby the ELRC to amend their annotation guidelines and account for larger amounts of data. Other fun things, the amount of text we have in EU languages, about 263 terabytes, or put another way, we have 2 trillion words of English and proportionate amounts of usage on the web for other languages. And we're actively translating 1 trillion words into English just to find matches. So I've also been asked to emphasize that we're not replacing your data. We're crawling everything we can find on the web. And the point here is to improve the coverage of MT at EC. And in general, we are producing big, somewhat noisy data. We do make efforts to clean it up, but the web is a mess. And the way we deal with noise is we throw things out. So if there's a sentence in your PDF that's broken at a page number and there's a number inserted in the middle, ideally we will detect this is a bad translation and throw it out. We're not going to try and manually fix up, and we can't afford to manually fix up, that this translation corresponds to this one across the page break, and maybe we should delete the hyphen at the end of the sentence. That sort of thing we're not doing at scale. We are crawling 500,000 websites, and each of them has their own special snowflake and eccentricities. And we're aiming to have big data And if there's a problem with some of the data, we throw it out. Which means we're not going to get as clean of data or as much data as you have available. The other thing is simply by knowing if you're translating e-justice, for instance, and you have in-domain data, you can make the translation system, customize that, and Google had the same data as WIPO had to translate their system largely, but they still got 6.4 blue points higher, and the reason is they were willing to customize that for patents and invest the effort into doing that. And that's really the difference that your in-domain data makes. My goal is to make that baseline go up much higher by having more data and increase the coverage, and that way you might be able to translate someone and they won't be harmonized. Okay, so that's the slides I have, but I will also think by funding, we currently have 6 different EU funding streams. The other thing that's, I guess, somewhat unique is there are a lot of companies, to be blunt, mostly American companies, who are now suddenly interested in actually providing cash for translation projects. And part of this is related to the digital single market. Amazon and eBay are building translation systems for products. Amazon translates their products offline. eBay does it on the fly. In Spain, for whatever reason, there are more buyers than sellers on eBay. In Germany, there are more sellers than buyers. And so eBay translates German listings into Spanish, which is in a sense part of the digital single market. It's not a complete solution. It doesn't cover e-procurement, but little bits and pieces of this are happening. Mozilla is interested in building in-browser translation that would happen on the client side and preserve privacy. So rather than sending your data to Google, it would stay on your machine. Intel, in this case, wants things to run fast on their processors. Makes a lot of sense. They want to sell more processors, but they also want us to be using theirs and not NVIDIA's GPUs, which, to be honest, is what we're using right now. Microsoft said, here, have some cloud credits. I grabbed $750,000 of Microsoft cloud credits. And we've been burning that on translating, say, 1 trillion words into English so that we can find every little translation on the internet. The Facebook use case is somewhat obvious. People want to talk to their friends, but also they have very weird problems in that it's informal and there's a lot of personal names in it. Google just wants things to go fast. They have largely the same system as everyone else does, and sometimes we beat them, and sometimes they beat us in the conference on machine translation. It doesn't have to be the case that your system is worse than Google. You can download systems from our website that are better than Google at Czech, for instance, right now. They are available under non-commercial license, but also the EU paid for it. So if you fall under that, then you can get our systems. Of course, we're a university, we can't really afford to install everything on your systems and set it up, but this code and the system is available to you. And these companies largely contribute under the same terms, that they just hope we build better software and make it open source. There's no specific deal that they get something from us over and above what anyone else gets out of the research we do. So yeah, I'll take questions.
Yeah, so have you considered using the common crawl instead of crawling the actual web?
Okay, so we are using the common crawl. And the common crawl is 60 terabytes a month. We've downloaded all 38 crawls since 2012, and they are sitting on Microsoft Azure right now, and they're being translated into English. The problem with common crawl is it's not deep enough. That if there's, for instance, the UN website, we would only expect to get about 100 translated documents from it if we restricted ourselves to the common crawl. So what we're doing in Paracrawl is we start from the Common Crawl, identify 500,000 multilingual sites, and then we target those with our own crawlers. Now, Common Crawl is 30 terabytes a month in raw crawls. The Internet Archive has 17 petabytes of crawl, and it's growing at 2 to 3 petabytes per year, which if you work it out is about 9 times as large, even in growth rate, than the Common Crawl. I don't have a place to store that yet, but they've agreed to share their data.
A very quick comment and then a question. The comment is about the quality assessment that you mentioned, about these 3% words. The idea behind it is to really ensure that what we crawl is high quality translations. If I go along the lines you mentioned, if you crawl more than 2,000 sources, which happened to us, and then you select 2,000 sentences, basically it means that you are selecting only one sentence per site, and this is very hard to assess the quality of the site translation. So this 3% is really something that has to be adapted to the context of your crawling and done case by case. So that's my comment. The question is, very often when you crawl, we end up with crawling sites that were translated using machine translation systems. How do you handle that?
Okay, so the first comment of yours, yes, that means manual evaluation of less than one sentence per site. I contend that the end goal of this is to improve machine translation quality at EC and in general everyone. And so actually, the end goal of this is produce an end-to-end translation system, and if the scores go up and if the human judgments of the translation quality go up, then that is a good thing. And doing intrinsic evaluation on individual sentences is only a proxy to get us to translation quality in the end. We do have automated systems that are looking for neural machine translation probabilities, for alignment scores, all the features that you would bring out. And what we're hoping to get out of the human evaluation is tuning data for how we should combine and adjust those features. Also, we do want to actually measure how much quality we have and have a number that's comparable to you. Okay, on the second point,
how you identify websites that you're crawling,
yes.
are produced using machine translation.
Okay, so there are actually papers about this. One of the nicest papers is Google Translate actually watermarks their translations. So if you hash the sentences in a weird way and then discover that the hashes fall in a particular range of numbers, then that is a watermark from Google that's reliable across paragraphs, not individual sentences. And they've published that hash function. So what they actually do when they're producing translations is they take an n-best list, they add this hash function, does it fall in this range, as a feature, and then they re-rank their n-best list at the end. So they might give you a slightly worse translation that has a watermark in that, and we can detect those. There's also techniques you can use to detect pure machine translations just from content. One of them is suspiciously high language model scores.
Thank you very much for your comparative studies between the various approaches. I was wondering if you have any idea or suggestion how the system or the approach perform where human is the loop, for example, post-editing. Are they similar or is one's approach better appropriated?
We're starting to do studies about post-editing time. A lot of time in post-editing is spent on fluency, so I would expect it to decrease, but I don't have a firm number for you. For automatic post-editing, there's definitely an entire track in the Conference on Machine Translation, but we don't have great data on post-editing the latest neural systems because they're too new.
The question is about whether when you're training your NMT systems, are you using the raw text or you also make use of some additional annotation?
When we train our, we typically use the raw text. The annotations we use are domain labels. Where did this come from? And there's also a paper about politeness and how you can modulate politeness. But for the most part, we don't use extra metadata.
So I was wondering on the level of, for instance, lemmatization, MSD tagging, and things that were previously attempted with SMT.
So for lemmatization, there's a paper from the Czech people at the Conference on Machine Translation, and they say you can get a blue point or so of improvement on doing lemmatized Czech. I wouldn't say it's mainstream right now. It just came out. A lot of people have been trying to do proper morphology things and failed to beat byte pair encoding, which is a relatively dumb way of segmenting things that doesn't follow morphology. We tried doing some flavor of that as well and gave up because the quality wasn't going up. However, lemmatization for the Czech people at least worked. They had a rule-based lemmatizer.
Thank you.
So what's a blue point, other than this conference center, of course?
What is a...
How do you calculate it?
Okay. Nice pun there. So a blue point is calculated by matching strings of 1, 2, 3, and 4 words with a human-produced reference. And it's based on the precision of those. So you want to have, and then there's geometric weighting that combines those together, typically with a uniform weight. It's done on the corpus level, so even if you have 0 4-grams in one sentence, you can still hopefully have a 4-gram match somewhere, and because it's a geometric, it's multiplied, so you don't get a blue score of 0. Also, it's based on precision with some clipping, so you get not how well did you reproduce everything in the reference sentence, but it's how much of your sentence appears in the reference. And it's a fraction of your sentence that's in the reference. That would incentivize having short sentences. You could thus just produce the, and at least hope to get some blue out of that. You probably wouldn't get any 4-grams, but you would get unigram matches. And there's a brevity penalty that says if you produce really short output, then it also takes points away. So it doesn't actually look as much at recall as precision. Is the stuff in your output supported by the reference? Blue is somewhat controversial. There's an entire metrics task on who can produce the best correlation with human judgments every year. Blue tends to lose. However, most people optimize their systems for blue and thereby overfit and game blue to the extent possible. Therefore, one would expect blue to have low correlation with human judgments because at that point, you're just measuring how much people overfit it. And then the trick is actually, if you optimize for a different metric, do you have the same problem? The other funny thing is people are less optimizing for blue now than they used to because it's more expensive to do that. It adds about a week to your training time. And we typically optimize for perplexity just trying to get each individual word correct. But blue is the old standard everything. These numbers I present here are based on human assessments, though.
Yeah, thank you, Kenneth, also for answering all the questions, but above all for this very, very interesting insights into the quality and neuro-machine translation and, of course, the connection to the data. Yeah, thank you very much.